Section 4.4 is called Everyday Forces, and our objectives are going to be to understand the difference between weight and mass, to discuss the normal force, including its direction and magnitude, to outline the many types of friction, and to discuss and understand the meaning of coefficients of friction. First, let's take a quick look at weight. The weight of an object is defined as the force that is exerted on the object due to gravity. So we call that Fg, meaning a force due to gravity. Now the force due to gravity is equivalent to the mass times the gravitational constant at that location. Now it's really important to be able to distinguish between the mass of an object and the weight of an object. Remember, the mass is the amount of matter that makes up the object, but the weight of the object, it's a function of the gravitational pull. So if you're on a different planet, or if you're at a different location on the Earth's surface, technically your weight changes because of your location. And we'll learn more about that when we look at Newton's universal gravitational law. Now, this explains why an astronaut that's walking on the moon only weighs like 1/6 of the weight as compared to its measurement on Earth. The magnitude of the acceleration of gravity on the moon is only 1.62, whereas on Earth it's 9.81. So it's about 1/6 of it, so this g value is 1/6 of the value on Earth, thus the overall weight of an object is less. Okay, you feel like you weigh less, even though you have the same amount of matter to make you up. The last thing we want to write down is that some books will call it W for weight. I recommend not doing that because W really stands for work, and as a unit W is watts. Okay, and remember this is a force, so the units in this problem are going to be newtons. Okay, newtons. Let's take a look at the first example. If an object's mass is 25 kilograms, what is the magnitude of its weight on Earth? What about on Jupiter, where the acceleration due to gravity is 2.64 times that of Earth? So let's start this problem by listing our givens first. The first thing we know is the mass is 25 kilograms. The second thing that we can see right away is that we are looking at this on Earth first, but then we're going to be looking at it on Jupiter. So we know that the gravitational constant g on Earth is 9.81 meters per second squared. Alright, what are we trying to figure out? What is the weight of the object on Earth? So we're trying to figure out what Fg is on Earth. And then we're going to do the same thing and find Fg but on Jupiter. So remember, Fg equals mg, so we just plug in 25 kilograms times 9.81 meters per second squared, giving us a weight on Earth of 245, roughly 245 and a quarter newtons. Now, we're suddenly on Jupiter. What's going to happen? Well, on Jupiter, the acceleration is 2.64 times that of Earth. So the force of gravity on Jupiter is really mg times 2.64, because this 2.64 is really multiplying by g, but we remember it doesn't matter. You can put it on the outside. You can put your parentheses if you want to. You can do this instead. You can go ahead and put your parentheses there and multiply g by 2.64 to get the new gravitational constant, then multiply by mass, but it doesn't matter. Again, multiplication is both commutative and associative, so the parentheses don't matter, and the order in which I multiply them don't matter either. So in the end, what we're going to get is really, think about it this way. It's really whatever it was on Earth, right? That's what Earth is, mg, times 2.64. So take this answer here and just multiply it by 2.64, and you'll get your actual value. Okay? Or you can go through all the steps. In the end, you're going to get 647, roughly, 0.46 newtons. So clearly the person weighs more on Jupiter because Jupiter's gravitational pull is much stronger than Earth's. So if you suddenly started walking around on Jupiter, you'd almost feel 3 times as heavy as you are on Earth. Now remember, in this problem, it asked us to find the magnitude, and that's what we did. We found the amount of the weight of the object. But if we were asked for the direction, we should remember that since we're on a planet, it's going to be toward the center of the planet. So we could say that this would act in the negative y direction. Again, because it acts down, because gravity's pulling you toward the center of the Earth. Let's take a look next at normal force. The normal force is defined as a reactive force that acts on an object in a direction perpendicular to the surface. Okay, so we have an object sitting on a surface. So let's say here's a desk. Okay, and we know that there's a box on top of the desk. Okay, and the box is sitting there on the desk and it's pushing down with a certain amount of weight. Well, the question becomes, what's causing this box not to fall through the table? And you're going to say, oh, the table is causing it not to fall through. But there's some sort of force pushing back up, and that's what's called the normal force. And it acts straight up out of the surface at a right angle to the surface. Okay, so this is called the normal force. And the reason it's called normal is because normal means perpendicular in 3 dimensions. So what I'm saying is that you can draw that right angle there. I could have drawn the normal force here and drawn the right angle in like that. There's the right angle. I could see it that way. I could draw the right angle in on the back side. But no matter what, there's going to be a right angle from this force. So it's like a building coming out of the ground. Every side of the building is at a right angle. So it's normal to the surface. Normal to the surface. So example 2 says, if an object is at rest on a table with a mass of 10 kilograms and you're trying to lift it with an upward force of 35 newtons, will it lift off the table? If not, what is the normal force exerted by the table? So let's think for a quick moment and make sense of this. The only time an object will ever be lifted off a table is if you can apply a force upward that's greater than, or equal to at least, its weight. If I could pull upward with, say, like 7 pounds of force, but an object weighs 10 pounds, then it's clearly not going to lift off the table. So we have to first start by thinking about, is Fp greater tan Fg? If Fp is greater than Fg, it's going to move off the table. If Fp is not bigger than Fg, well, then there's going to be some leftover force on the table pushing down, and then that's going to respond with a normal force pushing up. So we're going to see here that our normal force is not going to be equal and opposite our gravitational force, even if it is on the table, because we're trying to pull up on this box a little bit. So let's take a look at what's given in this problem. What I see is given in this problem right away is first the mass. The mass in this problem is given as 10 kilograms. The force pulling upward is given as 35 newtons. Gravitational constant is 9.81 meters per second squared. We are trying to find Fn if it stays on the table. If not, we don't do that part. So let's take a look. We've got everything acting vertically. So we can write that F net in the y direction, okay, equals ma in the y direction. But we don't know right away if this object is moving. If it's moving vertically, we'll have acceleration. If it's not moving vertically off the table, then we won't have acceleration. So before we go any further, let's quickly see if it is or isn't moving. The way we can tell is by calculating the weight. So let's go over to the side now and write a little note. The weight of the object, remember, is mg. The mass of it, we said, was 10 kilograms times 9.81 meters per second squared. So that tells us that the weight in this problem is actually 98.1 newtons. Okay, 98.1 newtons. That's the weight. Well, if the weight is 98.1 newtons, and you're pulling up with 35 newtons, you are not pulling up with enough force to lift it off the table. So it's not going to be lifted off the table. So that means that the acceleration is not going to happen. There's going to be no acceleration. So this is going to go to 0. So we could set that equal to 0. Now, let's take a look and think about this for a moment. Let's look at our y direction. How many forces are acting down? Well, it's just gravity. So we put a negative sign there for negative Fg acting down. We know that the normal force is pushing back up, but the normal force is being assisted by you, or the person, with Fp acting up also. And that's going to equal 0, because there's no net acceleration, because again, the object isn't moving. Let's continue going through this process. We were trying to find Fn. So let's go ahead and solve for Fn. Let's add over the Fg. Okay, again, add this part over here and subtract this part over here at the same time. So you end up with Fn equals Fg minus Fp. And let's make sense of this answer. Let's make sense of this answer before we actually plug in any numbers or anything. Okay, let's make sense of this. So here, the normal force would be equal to the weight if it was just sitting there on the table resting and there was no force being applied. So imagine your book sitting on the table. The normal force would just be equal and opposite the weight of the object. Now imagine that suddenly you walk over to the book and you try to lift it up a little bit. Well, you're kind of helping out the table. You're saying to the table, I'll help lift part of the weight of this and you help lift the rest of it. So it's saying, let's just subtract that quantity off from the weight, because the table is not going to feel the full weight of it. It's going to take away whatever you helped it out with. So let's go ahead and plug in our numbers now. The normal force in this case will be whatever the weight is Again, if it was just an object sitting there, that's what the normal force would be. But since you're helping out the normal force by pulling up, you need to take away whatever the force you apply, 35 newtons, giving us a result of 63.1 newtons as the normal force. So remember, this problem really teaches us that we won't always have a normal force that's equal to the weight if there's some other external force being applied in the vertical direction. So example 3 says a small object is stacked on top of a larger object and they are both on top of a table. So right away let's start by putting our table here. Let's put a large object and a small object. If the masses are 5 and 15, what is the normal force acting on each object? So this is a mass of 5 kilograms, this is a mass of 15 kilograms. And we want to find out what the normal force is acting on each object. So clearly we have two different normal forces because we're looking for each one. Let's start this problem first by looking at a free body diagram of each of these two objects. So let's start with the smaller object. A 5 kilogram box is simply sitting on top of the bigger box. So for it, we have the weight acting down. We'll call this FG1 for the first box. And we know that there's the normal force pushing back up from the lower box. We'll call that FN1. And we can draw the bigger box and realize, all right, well, we have the weight of the bigger box pulling down. And we've got the normal force pushing back up from the table. But for this problem, we have to remember that the little box pushes down on the big box. So we have to actually show that. So let's put a force pushing down on the big box. And what is that force? Well, it's pretty much the weight of this object. The weight of this object here is pushing down on this one. So this force here is the same as whatever this is, the weight of the smaller object. So FG1 is going to also go up here. So that's our free body diagram for this one. That's an FG1, okay? So we've got two different objects, so we're going to have two different sets of equations here for sure. They're both only acting in the vertical direction, so we don't have to worry about the sum of the forces and the y. They're not moving or anything, so we know there's no acceleration. So on the side here, let's just quickly write down our givens again. It's 5. It's going to be 15 kilograms. We know that the acceleration for both of these objects is 0. Or for all things in this problem, the acceleration is 0. And then the gravitational constant on Earth is 9.81. So let's take a look and say to ourselves, for the first object, the sum of the forces, or the net forces in the y for the object 1, is going to equal 0. So that tells us that Fn1 minus Fg1 is equal to 0. Again, just to reiterate, where do these signs come from? The sign of Fn is positive because it's pushing up. Fg is pulling it down, so that gets a negative sign. This is 0 here, even though it's really Ma. But we said a moment ago that A was 0, so that drops off. Let's go ahead and figure out, by solving for Fn1, what the normal force is acting on the smaller object. So solving for Fn1, it's simply Fg1 by adding the Fg1 over to the right-hand side. Now remember that the force of gravity is defined by the mass times the gravitational constant. So Fn1 equaling Fg1 can really be written as mass times gravity. The mass of the first object is 5 from up here. So that's going to be 5 kilograms. And the gravitational constant is 9.81 meters per second squared, giving us a normal force of 49.05 newtons. And this makes sense here because, again, what's going to push back up? That's 49, not 149. What's going to push back up on the smaller object the same amount as its weight, because it's in a state of equilibrium here. Okay, it's a state of equilibrium, there's nothing else pushing down on it. So we notice that these two are equal and opposite. Okay, so that's our value for Fn1. Let's take a look at the forces on the second object now. We've got the normal force, Fn2, acting up, so that was the first object. Second object, again, F net y equals 0. We've got the normal force for the second object acting up. We've got the weight of the second object pulling it down, and then we've also got the weight of the first object also being applied to it. So this problem is not very different from the last one. Here we had Fn1, Fg1. Now we've got Fn2, Fg2, but we've also got the weight of the first object pushing down on top of it. Okay, this Fg1 over here. Let's go ahead and take a look We want to find what Fn2 is, so we can simply add this over and add this over. So we get which is really equal to m2g plus m1g. Okay, the weight of the second object plus the weight of the first object. Now, notice here, you're really just adding the weights together, and that makes sense. If you sit on a chair, the normal force is no longer just the weight of the chair pushing back up, but it's the weight of the chair plus your weight acting on top of it. So we have to add together the weight of the big object and the weight of the small object, and that's what the table is really holding up. We had this number from earlier. This was 49.05, and this is going to be 147.15. And summing these two values together, we're going to get a total normal force from the table of 196.2 newtons. And this makes sense, again, because the objects are at rest. The bigger box pushes up on the smaller box with the equal and opposite of the weight of the smaller box, but the table pushes back up with the sum of the two weights of the boxes that are sitting on the table. Example 4 says a force of 100 newtons is applied to a box that's currently at rest on a table in the upward directions. If the mass of the box is 8 kilograms, will the box move off the table vertically upward? If so, with what acceleration? If not, what is the normal force provided by the table? So let's start just by making sense of this statement. If it does move vertically upward, okay, again, will it move off the table vertically upward? If it does, if it lifts off the table, what's the acceleration? That's the question. But if it doesn't, if it remains on the table at rest here, then what is the normal force? Clearly you can't have both of these. If you have a normal force, then you're not going to have the acceleration in the vertical direction because it would be off the table. Just to make that clear. So again, we have a diagram. Let's draw it. We have our gravitational force acting downward as the weight. We have a possible normal force acting upward. And we have a pull also acting upward. So again, there's a pull of 100 newtons acting upward. So let's write that down. Fp is 100 newtons. The mass of the box is 8 kilograms. Okay, that's the information that we have so far. So we have to think right away, all right, well, when will this object be lifted off the table? If the Fp is bigger than the Fg. Again, if the pull is greater than the gravitational force, then it's not going to be on the table anyway, so Fn will not exist. So we're trying to figure out whether we need this or not first. So let's take a look at that. Let's figure out, we know what Fp is, it's given as 100 newtons, so let's find Fg, and Fg is defined as the mass times gravity. Well, in this problem, the mass happens to be 8 kilograms, so we plug in 8 kilograms here. We multiply that by a gravitational constant of 9.81. So the weight of the object turns out to be 78.48 newtons. Now, and sorry, these units were meters per second squared, as always for our gravitational acceleration. Since the weight of this object is less than the pull, it's going to actually lift up off the table, so there's no normal force. So that's not going to be in the problem anymore, so we don't need it. Okay, again, that's the only reason that works, so we can get rid of this normal force here. Alright. If we get rid of the normal force, now we only have two forces acting up and down. We're trying to find what is the acceleration, so let's look at the sum of the forces. Why do we look at the sum of the forces? Well, we look at that simply because of two reasons. One, it's all we can do, to be honest. And two, we're looking for the acceleration, and the sum of the forces equals ma, a being the acceleration. So it just makes sense to do that. Let's go ahead and think about this. The sum of the forces. Well, we have gravity acting down, and we have the force of pull acting up. Okay, so let's take a look at this part now and continue here. That equals MAY. Let's solve this algebraically, even though you could plug in the numbers now, I guess, because you do know the numbers, but I'm just going to solve algebraically like we always do. So if we solve for the acceleration, let's divide through by mass. And we'll see that our acceleration is a function of the mass of the object, the gravitational constant on Earth, and the force of pull acting upward. Plugging in those three numbers that are given, we'll end up getting an answer for acceleration of around 2.69 to be exact. So the vertical acceleration is 2.69 meters per second squared. Example 5 says a person rides an elevator while standing on a spring scale, so a basic spring scale that we've seen before. What does the scale read if the person's mass is 10 kilograms and the elevator is accelerating upward at 3 meters per second squared? What would the acceleration of the elevator have to be for the person to feel weightless? Alright, so clearly we have to look at the situation. We've got a person inside of an elevator shaft, and that elevator shaft is accelerating upward. So we're looking at the forces on this person. So acting down is gravity still, and acting up is the normal force. Those are the only two forces acting on this. We have an overall acceleration of the elevator of 3 meters per second squared, a mass of 10 kilograms, and we want to figure out what the normal or what the spring scale would read. Well, remember, a scale is pushing back up with the same force that you're putting down, so a scale really reads the normal force. Okay, the scale is what's reading the normal force, so we have to find the normal force in a sense. So let's go ahead and look at that. We'll say the sum of the forces in the y direction equals ma. This is a in the y direction, so I should specify. We take a look here, we say, alright, sum of the forces, we've got normal force acting up minus Fg equals may, and we're trying to find the normal force, so let's add Fg over. And remember that gravitational force there, Fg, is really mg, so let's replace that with mg. So what we notice actually is this, and this is the interesting part. If you remember from when we started this section, when we talked about basic normal force, the normal force acts upward, usually opposite gravity, and only gravity, but because this object is now moving, it's not just gravity. We could see here that really the normal force is whatever gravity is, or the weight, a gravitational force, plus this acceleration that's kind of added into it, and that makes sense. When an elevator is moving upward, you feel your legs kind of like get, tense up a little bit because they have to withstand more force. So the normal force that your legs feel, the push back up when you're accelerating upward, is not just your weight anymore, but it's also the acceleration. So this number is going to be greater than whatever your weight is. You're going to feel like you weigh heavier. So when you're moving up on an elevator, you feel like you weigh heavier as well, your legs kind of tensen up to withstand that. So the normal weight of this person would be 10, the mass, times 9.81, or 98 newtons. But this turns out to be 128.1 newtons. Okay, that's what the scale reads. Well, the question then becomes, when would you feel weightless? Well, remember, the normal force is the measurement of your weight. So we're saying, when is this quantity going to be 0? Well, that could only be 0. Let's write it like this. It could only be 0 at one time. Well, here's the time. Let's take a look. Clearly, the mass can't be 0, or else the person doesn't exist. So we'll factor out a mass here, and we'll see that this is what we get. Well, G, remember, for forces, is just positive 9.81. So the only time this quantity, when multiplied by each other, the mass times the sum of these two could be 0, is if these two come out to be 0. So the acceleration would have to be downward, and it would have to be opposite that. So the acceleration of the elevator would have to be negative 9.81 meters per second squared for you to feel weightless. So remember this, the example where if you want to simulate weightlessness for like training for NASA and stuff, technically if you're in a rocket that's moving downward, with an acceleration of negative 9.81 meters per second squared, you would start to float as soon as you got to that acceleration. You would feel weightless for a moment. Because again, the normal force we said equals 0. And the only time that would be 0 is if this whole quantity here is 0. And that will happen when you add these two numbers up and you get 0 from them. Because again, this has got to be 10 or some quantity. It's a mass. Alright, so the friction force is a reaction force that opposes the applied force, or the force or the direction of motion for this example. And friction force is denoted by F subscript F right here. Okay, and again, the friction force depends on two things, the normal force and the surface contacts. Let's go over examples of why that is. So think about a chair moving across a room. If a person suddenly sits in the chair, isn't it more difficult to suddenly move the chair? Well, that's because what happened really is you put more weight on the chair, and so you increase the normal force, right? You push down on a chair more, normal force is going to go up, it's going to increase. So what we can say right away is that clearly the force of friction is definitely proportional to the normal force. So as the normal force increases, the force of friction is also going to increase. Now consider if you slide the chair across a tile floor versus a carpet floor. Across the tile floor, it probably moves nice and smoothly, but across a carpet surface, which provides much more resistance to the tile floor, is going to move slower. So the surface contact also matters, the surface contact. And we'll have something we can label that with, but it's some sort of experimental value between two surfaces. Let's take a look at static friction. Static friction is a resistive force that opposes the relative motion of two stationary surfaces. Let's take a look at an example. Imagine you have a desk here. Okay, and you want to push the desk, and you want to move it. And you push with 2 newtons of force, and it doesn't move. It still sits still. Well, that means it's pushing back with 2 newtons of force. Friction is pushing back. Now let's say you get another person to help you, and together you can push with 4 newtons of force. It's still not moving. Well, it means the desk is now moving and pushing back at 4 newtons of force. So when you're looking at static friction, what we'll notice right away already is that static friction changes as you push or pull more. So static friction on a table that's not moving can start at 0. And static friction can range. Okay, force of friction that's static, I should write FFS. Okay, can be arranged from 0 all the way up to whatever it is until you overcome that value. Okay, so it could be 0 at first if it's not moving, but eventually you might push with enough force. Let's say you get a third person and you push with now, let's say 7 newtons of force. And suddenly, as soon as you get to 7 newtons, so like 6.8 newtons didn't work, 6.9 newtons didn't work, at 7 newtons, the table just begins to move. So that would mean that the maximum allowable force is about 7 newtons. So that would be what's called FFS max. The force of static friction, that's the maximum allowable value. So in this problem, if it moves at 7 newtons, that's what FFS max is. It's the maximum allowable force before it begins to budge or begin to move. With kinetic friction, we'll notice that it's the resistive force that opposes the relative motion of two moving surfaces. Moving, as opposed to static friction where there were stationary surfaces. Now we have two moving surfaces. So, in this case, what we want to think about is the fact that when you get an object moving or just start pushing it, it's somewhat easier to keep it going once you've got it started. And that has to do with the idea of the difference between kinetic friction and static friction. And what we'll notice is that kinetic friction is much less than, or not much less, but it's less in general than static friction. There's one real simple reason. On a microscopic level, the surfaces that are in contact, they're pretty rough. They're like kind of jagged, actually. And we saw that with that little microscope zoom in. But we've got like a surface here and a surface here, and they're moving past each other. So that surface is moving that way, and this is maybe stationary. This is the floor. Down here, this is the floor, and up top there, that was say the leg of a chair, and it's moving over the floor. Those jagged surfaces, when they move together, they actually stick together at the contact point. So maybe like, here and here are stuck together. And you have to overcome that push initially when you have static friction. But once it's moving, it slides back and forth. But again, you're pushing this way, and there's some contact. Maybe these valleys like fill these little gaps here. That's what it would look like on a microscopic level. Well, you got to get this going. You got to break that contact. And this is adhesion. Okay, and this is the result of the electrostatic forces between the molecules on the surface, actually, between the two surfaces. So it's tougher to get something moving. Once you get it moving, though, it's pretty easy to keep it moving. So what we can really say for this part is that the force of friction for kinetic friction is going to be less than or equal to the force of friction for static friction. So static friction is always going to be a little bit bigger than kinetic friction or equal to kinetic friction, one or the other. Let's take a look at our formula now for friction, and this makes sense because we already spoke about this. We said that as the normal force increases, the force of friction increases. That's right here. So if this number doubles, that means the answer doubles. Well, what is this value here, the mu? You might be able to know already, but let's talk about it. Mu, again, is either static coefficient friction or kinetic coefficient friction. That's really the ratio or the experimentally determined ratio that relates the two surfaces in contact. So if you have like wood and sandpaper, you have a high mu value. There's a lot of friction there. Sandpaper across wood creates a lot of friction, which is what removes the wood and smooths down the surface until you have a fine surface, and then it's nice and smooth. But if you had, like, say, metal ice skate on ice, is very low mu value because the friction value is very low. So again, this value here is called mu, M-U, okay? Greek symbol, it looks like this if you were to draw mu. Mu S stands for static, mu K stands for kinetic. And again, because it's tougher to overcome static friction, again, the same relationship exists. Mu K, though, instead of FFK, mu K is less than or equal to mu S. So static friction coefficient of a surface or two surfaces in contact will be greater than the kinetic coefficient of friction between those same two surfaces. So example 6 is the following. A 24 kilogram cart initially at rest on a horizontal surface requires 75 newtons of horizontal force to set it in motion. Find the coefficient of static friction between the crate and the floor. So what the problem is that we have here is this. You push on the crate with 50 newtons of force, it doesn't move. 60 doesn't move. 70 doesn't move. 71, 72, 73, 74, until you get to just 75 and you break the static friction. So that's the maximum allowable static friction force that we're going to have in this problem. So again, we take a look at this problem, we think about it this way. We've got a pull this way or a push, doesn't really matter which one. Okay, some sort of horizontal force. And we've got the force of friction acting against the motion. We've got the weight of the object acting down. We've got the normal force acting up. I should specify that this is the static friction force because we're looking at the instant before it moves. Because we're trying to get it just to move. And since we're looking for static friction, it can't be moving. We can't look at things with motion when you're looking at static friction. So we have no acceleration. So we could say that the net force in the x direction is going to be ma, but the acceleration is 0. It's not moving. It's the instant before it moves. So we've got negative friction, we've got a positive push, and that equals 0. Well, we can go ahead and think about, we're trying to find the coefficient of static friction, so μs. So let's replace FFS with our formula. Remember, force of friction is mu times Fn plus Fp equals 0. Again, I'm replacing this force of friction with mu Fn. It's static friction, so I put the static friction coefficient. So it looks like we're going to solve for mu. That's what we're looking for, the coefficient of static friction. But we don't know what Fn is. We know Fp, that's given. Okay, that's given us 75 newtons right there. We don't know Fn. We need to figure out Fn. Well, there's nothing to do with Fn in the x direction. Here's Fn, it's in the y direction. So we wrote the sum of the force in the x. Now let's write the sum of the forces in the y direction. We've got F net in the y direction equals ma, but it's not moving, again, vertically. It's being pulled horizontally, so there's no acceleration vertically. In the y direction, we've got gravity acting down and the normal force acting up, and that equals 0. Well, we want to figure out what the normal force is so we can substitute it in here for normal force. So let's go ahead and solve for normal force. Adding gravity over, we get the normal force equals mg. Well, why did I put mg? Because this is really mg. So this is really negative mg. So if I want to get rid of mg, I add it over to the other side. So when an object is stationary and there's no vertical acceleration, like this example here, and there's no other applied forces vertically, remember this is our general rule that the normal force is equal and opposite to weight. So we plug in mg right here. So we're going to take this, I'll circle it in blue, plug it in right there for Fn. So we're going to rewrite this equation here, we'll write it down here. That equation becomes negative mu s times mg plus Fp equals 0. And now all we need to do is solve for mu s. Let's add that whole term over. We'll leave Fp alone on the left-hand side. We'll add this whole thing over because it's currently negative, so that mu s becomes positive, and divide by mg. I'm just going to erase the mg, divided by mg. And that's what mu s is equal to. We know Fp. Fp is given in this problem as 75 newtons. We know the mass of the crate is given as 24 kilograms. We know the gravitational constant on Earth is 9.81. We can plug in for those three values, giving us a mu s value. Remember to put parentheses around these, by the way, in your denominator when you're using a calculator. We get a mu s of 0.319. And just as a quick sanity check, remember that our coefficients cannot be negative, and we have a positive coefficient of static friction. Let's take a look at objects that are pulled at an angle. So we'll say when objects are pulled at an angle theta, so let's draw that. Here's a pull on an object, Fp, at an angle theta. We have to break the force into its perpendicular components. So we need to think about remembering the fact that a force at an angle, just like a velocity at an angle, has components Fpx in blue and Fpy in red. Now remember that if theta is measured with respect to the horizontal axis, meaning this is theta right here, here's the horizontal axis, here's the angle theta, then we can say that Fx is equal to F cosine theta, and Fy, this part here, is equal to F sine theta. Same rule that applied from velocities, and I'm not going to go over the derivation again, but just remember the same rule applies. to our initial velocities when an object is launched as a projectile at an angle. So example 7 says 2 students are sliding a 225 kilogram sofa at a constant speed across a wooden floor. It should say across a wood floor, not as wood floor. One student pulls with a force of 225 newtons at an angle of 13 degrees above the horizontal. So let's put this box here, and it says they're pulling above the horizontal. So here's the pull, and we'll say they're pulling at an angle above the horizontal. So we'll call that FP1, and we'll call that theta 1. And let's write down what those values are. FP1 is 225 newtons, and theta 1 is giving us 13 degrees. And again, it's above the horizontal. The other student pushes with a force of 250 newtons at an angle 23 below the horizontal. So imagine you're going to push a table across the floor. You would push down on it like that, really. Okay, at 23 degrees below its horizontal. Well, here's its horizontal now, below the horizontal. See how that's below as opposed to this one, which was above. This is theta 2. And theta 2 is given as 23 degrees, and the force applied there, FP2, was given as 250 newtons. The question asks us, what is the coefficient of kinetic friction between the sofa and the floor? So we're at a constant speed, which is really important to notice, so that our acceleration must be 0. We know it's not moving vertically right now. We're pushing it horizontally here. So the acceleration is going to be 0 meters per second squared. Again, the mass was given as 225 kilograms. So there's a lot of givens for this problem. And what are we trying to find? We're trying to find mu k. That's the question. Where does that come from? Well, that comes from the fact that friction is acting against motion. And we also have gravity pulling down. We have the normal force pushing back up. So we've got a lot going on in this diagram. What we need to do is remember that this really, FP1 is really this in the x, FP1x, and this is really in the y direction, FP1y. And when we do that, we can now only look at those two components of the forces that are written in blue. We can mentally get rid of this entire thing here by representing it like that. And the same thing goes for this part over here. We'll notice that this is going to be our FP2y, and this would be FP2x, allowing us to get rid of this portion right here. So what we've done is realize that we've got a lot going on. In the x direction, we've got FP2x, FP1x, and the force of friction pushing back. Remember, both people are pushing to the right, so those are both to the right. Notice both those arrows, and friction is pushing back. This first person was pulling upward at an angle above the horizontal, so their force is up. But the other person was pushing, remember, pushing below the horizontal at an angle below the horizontal, so this portion is down. So this is acting up in the y, this is acting down in the y. Fn is acting up in the y direction right here, and Fg is acting down in the y. So we've got a lot going on. And remember, we're looking for mu k. Mu k is embedded inside of ff, because ff is defined as mu fn. So really, we're going to end up looking for mu k in the x direction, but there's a good chance that we're going to take a look at fn again, like we did in the last problem, in the y direction, and transfer it over into the x. Let's take a look at our equations of motion now. We will start in the x direction. In the x direction, we've got friction acting backward. We've got FP1x acting forward. We've got FP2x acting forward. And since it's moving at a constant velocity, the acceleration is 0, so it's m times 0. So this is just 0. Let's write what we know. This is really mu k Fn, remembering that friction is always defined as mu Fn. FP1x is the same thing as FP1, but we have to multiply it by the cosine of theta. So we have FP1 cos theta 1, because we're looking at the first angle, plus FP2 cos theta 2, and that equals 0. Well, already, take a look, the only thing unknown is mu k. So we can move this over and move this over by subtracting them both over, and then divide by Fn. Now, we could also just move this whole quantity over here. That'll make it easier because it's already negative. That'll make it positive. So let's do that since it's easier. So we'll leave the FP parts alone. And move the other part over like this by adding them over. And then we'll divide by Fn on both sides. And when we divide by Fn over here, those Fn's cancel, so they pretty much go away on the right-hand side, leaving us with mu k equals that whole expression over Fn. But the problem right now is that we don't have Fn. And remember, Fn occurs in the y direction, so let's take a look back up real quick. So we want to really figure out, okay, here's Fn, here's Fg, we've got Fpy up, Fp1y up, and Fp2y down. We need some of the force in the y direction with those four forces. We can solve for Fn in the y, and then we can take that Fn quantity, the expression we get, and we can go ahead and plug it in right here for Fn. But we need to remember that the solution is fully generic right now. We could plug in numbers to get an answer, but I'm going to try and keep it generic because when we get to inclined planes, we'll see that generic solutions work much better than numerical solutions, because numerical solutions sometimes actually won't work because you'll have a missing piece of information. So let's write our sum of the forces in the y direction equals 0. Well, that tells me we've got gravity acting down. We've got Fp2y acting down. We've got Fp1y acting up, and we've got the normal force acting up, and that equals 0. Let's plug in what we know. So substituting in, we're going to have negative mg, again mg is really what Fg is, minus Fp2 sine of theta. Oops, let me fix that sign. And we'll put theta 2 because the second angle we're looking at, plus Fp1 sine of theta 1, again the y component of Fp1, plus the normal force, and that equals 0. So let's solve for the normal force by moving everything else over to the right side. Leaving the normal force alone on the left side, we'll move all of these other terms over here to the right-hand side, okay? So actually it's only 3 terms, not 4. I drew 4 lines there. And that equals positive mg plus Fp2 sine theta 2 minus Fp1 sine theta 1. And that is our generic solution for the normal force. We can take that quantity and we could substitute it in right up there for the normal force, giving us the answer for mu k, because we know every value. Now let's go ahead and figure out our generic solution for mu k by plugging that in. We'll try and carry this all down in one line. So we've got Fp1 cos theta 1 plus Fp2 cos theta 2 all over. That's from up here, remember? That's where I just got all that. And I'm going to put that over Fn, but Fn is this. So I'm going to put this entire thing right here in the denominator right here. And remember that that equals mu k. So at this point it's just plug and chug. You're plugging in the numbers and let your calculator run through the problem. Please remember that with this solution we have to be cognizant of our parentheses because you're dividing by an entire denominator. So when you put that in your calculator, you can do all the numerator work first, then divide by the denominator, or just put everything in its parentheses like so. You'll end up getting a mu k value of 0.199. Okay? So these surfaces are most likely smooth or treated so that they slide easily, like metal on wood. Or it's possible that there's like Teflon underneath the couch leg so that there's a low coefficient of static friction. Teflon allows surfaces to move smoothly across one another, which gives us this low value of kinetic coefficient of friction. Example 8 says a student moves a box by attaching a rope to it and pulling with a force of 90 newtons at an angle of 30 degrees above the horizontal. The box has a mass of 20 kilograms, and the coefficient of kinetic friction between the box and the sidewalk is 0.5. Determine the acceleration of the box. So clearly it's going to accelerate if it says determine the acceleration. So let's take a look at our free body diagram to start. For this problem, we've got our box here being pulled at an angle, Fp, and an angle theta. Only one pull, so one theta is needed. We've got the normal force acting up. We've got the weight acting down, and again we've got friction pulling back, and it's going to be kinetic because it's moving. The acceleration is going to be the right in this problem, okay? Now, let's list our givens. We've got a pull of 90 newtons at an angle of 30 degrees above the horizontal. We've got a mass of 20 kilograms. We've got a kinetic coefficient friction of 0.5. And now let's remember to break up FP into FPX and FPY. So we've got FPX and FPY. We can kind of get rid of this now. Remember, that's not really there anymore. So let's take a look at the sum of our forces, and remember that we are looking for AX. That's the question we're trying to figure out. So we're clearly going to have to look in the X direction. But again, there's a good chance we're going to look at our normal force from the Y direction. In the Y direction, we'll take a look there. We've got that equals ma, but the acceleration of this box is 0. So F net in the Y direction, we've got weight acting down. We've got the normal force acting up. We've got that pull, FPY, acting up, and that equals 0. So there's a good chance we have FPY. We can figure out what that is. We have FG. So we're going to probably solve for Fn again. Let's go over to the X direction, though, first to see what's going on there. We'll leave a little space. Well, in the X direction, we've got friction acting backward. It's a negative FFK. We've got the pull acting forward. That's a positive FPX, and that equals MAX. We are looking for AX. Let's plug in what we know in the X direction, then we'll go back to the Y. Let's continue this down here. The frictional force is kinetic, so it's mu K, Fn. Oh, take a look. Fn is there again. We need to know what it is. And FPX is really FP cosine theta, and that equals MAX. So we want to figure out the value of AX right here. Well, to do that, we divide by this M, which is pretty simple, but the issue becomes next, if we divide by M, we have FP, we have theta, we have mu K, we don't have Fn again. So we're going to need this Fn. So we should probably solve for Fn up here, and then plug it in down here. Okay, we can solve for AX by dividing by M first, but it really doesn't matter. I would rather just solve for Fn first and plug it in down here. So I'll do that up here in blue. We're going to replace Fg with negative mg right there. That negative Fg becomes negative mg plus Fn. Fpy is really Fp sine theta, and that equals 0. And let's solve this for Fn by adding mg over to the right side and subtracting Fp sine theta. So this expression right here is going to go in for Fn right here. So if you've noticed by now, Fn is indeed just like time when we looked at projectile motion. Fn is our linking variable. A lot of the time when you look at projectiles, you solve for the time in the vertical direction and you link it to the x direction. Well, if you have a variable in both directions, again, like so, we can link it and use it in both of those cases. So let's plug in. But remember, we're looking for AX, so let's divide by M. So I could just erase this M right here and divide the whole thing by M. Remember, that's AX over here. It's AX. So that's our generic solution for the acceleration. If we go ahead and plug in, we'll end up getting a number of 0.117 meters per second squared. Alright, let's take a quick look at inclined planes, and these can be confusing at first, but it's really not that tough once we come up to a conclusion about the force of gravity. So let's talk for a moment. First, we have to start by thinking about the inclined plane surface as the x-axis. So here's the first step. And if you don't do this, you're going to be lost, but you have to think of it this way. This is your x-axis now. Okay, and this is your y-axis right here. And I know that's weird, but you have to think of it this way. So they label this with the x-axis, and that's your y-axis. If you do it this way, it makes it pretty simple because a lot of the forces now act along the x and y axis. Remember, the normal force is always perpendicular to the surface. So the normal force will end up acting up this way. The force of friction will act against motion. Since motion is down the plane, friction will act up the plane. So that makes two of my forces act along the axis. But the problem is that gravity acts straight down still. So since gravity's acting down, like this, and we're really looking at the plane like this, it's like gravity's acting at an angle. So we need to break gravity up into its components, into its x component and its y component. But the problem is that we're usually using the angle with respect to the horizontal axis. So usually we're looking at this angle right here. Okay, but the problem is that if we make this triangle right here, we're going to see that that's not the angle that's given. We're given the complementary angle of that angle, which is 30 degrees. So this angle here would really be 60 degrees, and that's the angle we want to use. So whenever we go ahead and go to break up our sine and cosine components, so we want to find FGX and FGY, we would usually use sine of theta and cosine of theta. But since theta for inclined plane problems is the theta that's given as the angle of the incline and not the angle we need, we have to actually use 90 minus theta. Because remember, the angle that we need is that little angle in here, and I'll point to it right now. That's the angle we're looking for. Same thing goes with this part, and I'll draw over it in blue. This right here is gravity pulling down. This is our force acting this way. So if we connect this triangle like this, sure, this is, 45 right here, this angle, that's 45, but we want this angle right here. It happens to be 45 because 90 minus 45 is 45. But here, this is 60 degrees, that angle right there, but we want the angle that's not 60 degrees. We want this angle right here, which is 30 degrees, because remember 30, 60, 90 triangle. So in the end, we end up using 90 minus the angle we're looking for, given theta. That's our incline angle. So here's our correlation that we want to write. If we want to look at our sum of the force in the x direction, we're going to need to know what FGX is, because it's got a component. Remember again, the force of gravity acts straight down, but its component acts down the ramp, so it's going to be a negative quantity always. And this is going to act down this way as FGY. Well, FGX, remember, is normally whatever the force is times cosine of theta, but since we're on a plane now, we're going to use 90 minus theta, since theta is given as the angle of the inclined plane and not the angle that we need. And in the y direction, FGY would normally be FG sine theta, but it's going to be 90 minus theta. So if there's a rule you need to remember, it's this. For inclined planes, instead of using the incline angle that you're given in most problems, you need to use its complement, 90 minus that angle, when you break the gravitational force into components. So again, to summarize, when working on inclined plane problems, do two things. First, tilt the axis so that the x-axis is parallel to the surface of the plane and the y-axis is parallel to the normal force coming out of the plane. And break weight into its components using the following rules. FGX is FG cos 90 minus theta, and FGY is FG sine 90 minus theta. And remember that FG is really mg. So FGX is going to end up being mg cos 90 minus theta, and FGY is going to end up being mg sine of 90 degrees minus theta. Example 9 says a 91 kilogram refrigerator is placed on a ramp and that the refrigerator begins to slide when the ramp is raised to an angle of 34 degrees. So here's our ramp and the refrigerator right there. And it starts to slide down the ramp when the angle theta is 34 degrees. What is the maximum static friction force that the ramp can supply? And what is the coefficient of static friction? So again, we know the mass is 91 kilograms. We're trying to find the maximum static friction force. And then from that, we're trying to find the static coefficient of friction. So in this problem, remember, we're looking at the instant before it begins to move. The instant before it begins to move. Okay, and we have the angle theta. So let's take a look at this diagram and look at all the forces. So remember to label your y-axis like this and your x-axis like this. So the x-axis is up and down the ramp. So up the ramp is positive and down the ramp is negative for the x. Out of the ramp is positive for the y up here, and into the ramp is negative for the y. So we can still write some of the forces. And we're looking at the instant before it begins to move, so the accelerations are still both going to be 0, okay, in both directions. So it makes our equation a little bit easier. So in the x direction are some of the forces. We have F net in the x equals 0. Well, F net in the x, what's acting down the ramp? Well, it looks like gravity's acting down the ramp. Let's draw a free body diagram here. Well, here's gravity normally pulling down, but remember that we need to break gravity into its components. So it's got an FGY component and an FGX component. So we don't really need this anymore, but we have to remember that when we're looking for FGX, okay, we have to use FG cosine of 90 minus theta from our rule that we came up with a moment ago. Now we've got friction acting up the ramp. So let's draw that in the diagram now. That's static friction. And then again, the last force we have is the normal force pushing out of the ramp. Again, always perpendicular to the surface, hence the word normal. So in the x direction, all we've got is gravity acting down the ramp. So negative FGX. It's pulling us down the ramp. That's the negative x. This is up the ramp. This is the positive x direction. So we end up putting a positive sign in front of our force of friction. That equals 0. So remember, the force of friction can be like 10 newtons as you're increasing the ramp, then you increase the ramp a little more, then the force is 20 newtons and it's holding, then it's 30 newtons and it's holding, until you increase the angle enough that the force of friction is overcome by FGX. So we're really finding FFS max right now by adding this over. So let's go ahead and do that. FFS, we add it over, we add the FGX over to the other side, and remember that FGX is mg cosine of 90 minus theta. So the force of friction, of static friction rather, that's allowable for the ramp is mg cosine of 90 minus theta. That ends up being a value of 499.2 newtons. Okay, that's our first part. Then it said to find mu, the static coefficient for friction. But that's what this comes into play. This is really mu times Fn. So we could set that equal to 499.2. But the problem is that we don't know what this Fn is. Even though we kind of do. Let's go back and look at our y direction. In the y direction, we've got Fn acting up, and we've got FGY acting down. So if that's the only thing happening, let's write our y direction, and we'll use it back here in a moment. So we could say that the sum of the forces in the y direction is 0, because it's not moving off the ramp. There's no acceleration. So this tells me that, again, Fn is acting up in the y direction, FGY is acting down, that equals 0. So Fn ends up equaling FGY if I add this over as a positive. So this tells me that Fn, replacing FGY with mg sine, and remember to use 90 degrees minus theta. So that's what Fn is equal to. So we could replace that up here. So we could say, well, this is really just mu s times now whatever Fn was from down here, mg sine of 90 minus theta, and that equals this quantity of 499.2 newtons. So to get mu s by itself, divide by the quantity mg sine 90 minus theta. So let's just do that. Okay, and let's get rid of this here because we divided by the whole thing. And that's what mu s turns out to be, this expression over here on the right. So if we go ahead and plug in our numbers, we can solve for that expression. We'll end up getting a value of 0.675. 0.675. Now, what's really interesting to look at is this, and this is where it gets kind of cool, and you got to go back. Take a look back up here when we had force of friction static. This was the line we want to take a look at. And I'm going to rewrite this line over here, but instead of force of friction static, I'm going to write mu s Fn, because this is really that right there. And I'm going to say that equals this quantity still. And now, a moment ago, we replaced this Fn with its equivalent or expression from the y direction, which we calculated for Fn to be this expression. So if I take this expression down here that I'm currently circling, and I place it in right here, and then I divide through by it, I'm going to have mg cosine of 90 minus theta over Fn as my answer, but that's this, mg sine of 90 minus theta. So I'm going to take this equation here, and I'm going to plug in this expression into it. So I'm taking this, and I'm plugging it up here. But before I do that, let's divide by Fn to put it over here, and we can see how it's much more easy seen. So now we replace it right over here instead. And we end up getting, for this expression for mu as a generic solution, if we wanted, mg cos 90 minus theta over mg sine 90 minus theta. Well, what happens to the mg's? They drop off. So it turns out that mu s, the static coefficient of friction on an inclined plane, is independent of the mass. The mass doesn't matter. It drops off. So we could have done this problem without the mass if we were only looking for the static coefficient of friction, but we happen to be also looking for the maximum allowable, which we got earlier as 499.2. So we could use either solution, but again, in the end, what we'll end up getting for mu s is 0.675. Okay, and you'll learn in your Algebra 2 class that cosine over sine is really defined as what's called the cotangent, or 1 over the tangent. Example 10 says that a box slides down a 30-degree ramp with an acceleration of 4.5 meters per second squared. Find the coefficient of kinetic friction, mu k. Well, let's try and think about last problem. In the last problem, we realized, oh, you know what? It seems like for these problems, we don't have to worry about the mass, and we're not given the mass, so clearly that must not be involved. So let's draw a free body diagram again. Here's our box on the inclined plane. We've got gravity acting straight down, but let's break it into its components. Remember, this is really FGY, and this is really FGX. Here's our angle theta right here. Here's our force of friction, and it's kinetic friction because it's moving. And here's our normal force coming out of the plane at a right angle as always. So in this problem, we don't really need FG right here because we broke it into its components already. All right, let's take a look. Our givens. Angle of theta is 30 degrees, and the acceleration in the x direction is down the ramp. Now this is interesting. We need to make it negative 4.5. And if you forget that part, your answer is going to come out to be a little bit weird, and you'll realize that it's wrong. So you need the negative because it's down the ramp. And remember, we're considering that this is the x direction up the ramp, and this is the x direction down. Okay? So let's take a look at our x direction. We've got negative FGX plus FFK equals MAX. We're trying to find mu k, so it means we're probably isolating FFK. So let's move FGX over. We got FFK equals MAX. Whoops, that needs to be a little x for subscript. Plus FGX. So I'm again moving this over here by adding it. Let's plug in what we know. Remember that FGX is really always going to be mg cosine instead of theta. Remember, it's an inclined plane, 90 minus theta. So that's what FGX happens to be there. We plug it in. And FFK, though, is really mu k times Fn. So let's go ahead and replace that with mu k Fn. So again, as always, Fn turns out to be our linking variable. So dividing by Fn on both sides, and I'll just erase it on this side and leave that with just mu k. So that's our answer for mu k, but clearly we need Fn, so let's go to the y direction. The object isn't floating off the ramp by any means in the vertical direction, so we can say F net equals ma, but since it's not floating, a is 0. So in the y direction, we've got the force of gravity in the y direction acting down, and the normal force acting up out of the ramp, and that equals 0. Let's solve for normal force in that expression, giving us that normal force equals FGY. Okay, again, by adding this over, and then replace FGY with mg sine of 90 minus theta. So we can take this expression here, which represents Fn, and plug it in right there for our final answer for mu k. So mu k turns out to be max plus mg cos of 90 degrees minus theta all over mg sine of 90 degrees minus theta. So for this problem, since m is in all of the locations, it's in all three terms. Remember, it's in both terms in the numerator, so we can technically factor out m out in front. And there's m here, they all can just cancel off. Okay, and if you can't see that, factor out the m on top, and then cancel the m on the top and the bottom, but they all drop off. So our final solution is ax plus g cosine of 90 degrees minus theta all over g times sine of 90 degrees minus theta. And doesn't this look familiar to the static friction answer? Sure it does. Take a look. And this is what's so awesome about this. Here, If the acceleration were 0, it's not moving. So it would be static friction. So drop this off for a second. It's the same answer as last time, because then the g's would cancel. Again, if there was no ax there, then you could cancel those g's and end up with the same answer we had last time from us. But ax isn't 0 in this problem, so we can't drop ax off. But again, if it weren't moving, we'd be looking from us, really. We'd be looking from us instead, and we would end up with the same answer, because ax just drops off. But it doesn't just drop off, so let's go ahead and take a look at what our actual answer is. Let's plug in for ax since it's moving down the ramp, and it was down the ramp, so that's a negative value, remember. So that'd be the negative 4.5. Plugging in for theta of 30 degrees and g of 9.81, we're going to get an answer for mu k of, it looks like, 0.0477. So since this value of the coefficient is much less than 1, these surfaces are very smooth. So we're looking like, maybe like metal on ice. And finally, one last time, remember that our answer, mu k, is not a function of mass. Mass drops off. It is a function of the acceleration and the angle. So if we had no acceleration again, if this dropped off, it means the object isn't moving. This becomes mu s, and this is our answer. The same answer we got from us in the previous problem. Your homework for this section is from 3 different pages.